Good evening, everybody. Could you hear my voice, and also can you see the PowerPoint on your screen? Say yes if you do. Okay, that's good. Now I'm trying to repeat, right, for a few slides in the chapter 8 because we have lost our content, right, in the last lecture. Now, chapter 8, Earth retaining structures. At the end of this chapter, you should be able to identify different types of retaining wall. In fact, there are many kinds of different retaining walls in Hong Kong. And also you should be able to analyze and design the common retaining wall systems. Of course, for some simple retaining wall structures only. Now, earth retaining structure are usually the vertical or nearly vertical walls to retain a height of soil or even a rock. The purpose of the retaining wall is to arrest, right, the wall from movement because it's subjected to a very heavy or high horizontal force behind the wall due to the earth or due to the soil. And then the retaining wall will transfer the horizontal forces, right, down to its footing, so that under the footing, it will be eventually supported by the ground under the footing of the retaining wall. So the retaining wall is intended, right, to limit, right, to limit, very important, deformation. We don't expect any excessive movement of the wall due to the displacement of soil behind the wall. And the second point is to make sure, right, the structure will not be overstressed at any parts of the wall structures. In other words, it should be stable and it should be strong, right? These are the two main criteria for the design of the retaining wall, particularly when the retaining wall is very high. In Hong Kong, we have, we are short of flat pieces of land, so the government and the developer are trying to cut pieces of land into the slope. And of course, the slope will be finally be either supported by the retaining wall or you have to cut a very steep slope. And then you have to apply slope stabilization measures. So in Hong Kong, it's very common to see very high retaining wall. And also you have, in parallel, you have a new slope, right? You have either a retaining wall or a very high and steep slope next to our wall or next to the building structures. Well, there's a very authoritative document issued by the Geotechnical Engineering Office, the Geo Guide 1. Now, this Geo Guide 1 will outline, right, the fundamental requirements in terms of stability of the wall, the stiffness, and also durability, and many other serviceability requirements, right? During the construction stage, or even you have what parameters or what aspect you should detail design during the design stage. Now, in the limit state design approach, we have got two important limit state. The first one is the ultimate limit state, right? Here. the ULS. Now, the ULS, or the ultimate limit state, is the state at which a structure may fail, right? Under the loading or under other kinds of movement and so on. We don't want the structure will be, toppling over or tilting or the settlement is too much, right? So all these are the ultimate limit state. And there could be, some severe structural damage incurred, right? If the ultimate limit state requirements are not met. And also in the other important aspect of consideration is the SLS, the serviceability limit state. Well, the SLS, I think you should be familiar with these two concepts, right? ULS and SLS in your, the design of structures, right? Whether RC or steelworks. Now, SLS means the state at which there will be some situation that the structure may not serve you well. For instance, there may be some unacceptable cracking, or the deformation is, is too excessive, despite there is no structural collapse, but the deformation is too much. Or for the retaining wall, if the movement of the wall is too much, well, we may say that the SLS may not be met. It's not up to the standard, right? Types of retaining wall. Now, retaining wall could be classified as, the externally stabilized, okay, or the internally stabilized. So whether internally or externally stabilized. Right? Now we will concentrate on the externally stabilized system. Okay. So that is the major system, right? We are going to discuss in the following slides. Okay. Now for here, right? Now before we're going to talk the externally stabilized system. What are the internally stabilized? In this system, the soil will be reinforced like the concrete. So internally stabilized means that, suppose you got a structure there, a wall, right? Or a slope, right? Say there's a wall. Okay. Now, this wall could be made up of reinforcement. What sort of reinforcement? Well, the soil could be mixed with the cement, right? Say it's the cement. Or even you have inserts, right? Input some layers of plastics. Sometimes it's called the geotextile. Right? Geotextile. Layers of the geomembranes, right? Layers of plastic material, right? We have different engineering properties, right? So you are going to reinforce sometimes called the reinforced earth, not concrete, right? Here. Now, that's the internally stabilized. In other words, you are trying to mix the soil, right, together with some sort of reinforcement, whether it is made from cement or even the plastic material. So that is the internal reinforced, internal stabilized system. Now, of course, this is a very special topic. For the externally stabilized system, there's a physical wall structure right here, say in situ wall, and also the gravity wall. What's the in situ? In situ means RC or concrete, right? Okay, cast in situ, right? Cast in situ. And here the gravity wall, right? The gravity simply by the weight, right? The weight. So you have the, the massive concrete. So that's massive concrete. So you got a wall here, right? Very heavy trapezoidal, right? Concrete, plain concrete, right? Without reinforcement. So this wall could stand up very stable because its own weight. And then you may have the RC, right? The cantilever retaining wall, right? The RC. So you got a wall here, right? So you got a wall here. Right? So that is the concrete. That is the, the plain concrete. And here you got the RC. So you have to fix reinforcement and then pour the concrete, right, to make a in situ RC cantilever retaining wall, right? And you may also have the counterfort, right? We'll come to that later, right? What's the Gabion? Gabion means, you use the wire mesh, steel wires, right? So you got this wall here, right? And that's the soil, right? You got this wall. There's, there's the slope, right? And then this will be still the cage, right? The steel wires cage, right? Sorry, cage. You make a cage with steel wires and then put the rocks, right, inside that cage. So you got the rocks here, right? And then that's your steel wire cage. So that is steel wire. So you have a box, right, made up of steel wires. And then inside the cage, you put all the pieces of rock inside it. And by stacking, right, stockpilings of individual steel wire cages, then you will have a very heavy gravity wall there. So that is the Gabion. And also you may have the crypt walls. The crypt walls, right? Crypt walls means that, you got pieces of the, the precast, right? Precast concrete elements, right? That's the precast beam element, precast concrete elements. And then you're stacking over, right, a certain height. And then inside you infill with the soil, right? So it also becomes a very stable structure, right? That is taking advantage of its heavy weight. So it's the gravity wall. Right? Okay. Now, on the other hand, you may have the in situ wall. Well, you may have the steel ship piling, right? you have the steel section, right? The steel sheet piling. By interlocking the individual pieces of steel sheet piles, and then you can build up a very high and thin, right, retaining wall. Of course, you have to drive, right, the sheet pile deep into the ground. So you should have a, that is, the ground surface. That's the basement of the excavation. So it depends on the depth of penetration. Depth of penetration. Deeper the penetration depth, it will give you a firmer, right? A firmer support, right? To retain the height of the soil. So that is the height of retaining wall. And that is the depth of penetration. Right? For greater height to be retained, you have to drive the sheet pile deeper, right, into the ground. Okay, so that's steel sheet piling. And you could also have, rows of the ball pile, right? Ball pile. Ball pile. You know what's the ball piles, right? 鑽孔裝啊. So you drive the piles, and then very close spacing. So that's a pile wall. It means a wall made up of piles, right? Running parallel to each other, so that you have a very wide and tall and strong piling wall, right? To resist the height of soil, right? To retain very greater height of the soil. Right? So you have the pile wall. Okay. Now, sometimes you have this word, right? Blaze. Do you know what's blaze? You know what's blaze? Blaze means that if the retaining wall is too high, you have the sheet piling, and then you should have, use the different levels of struts, right? Structing, right? Right? Multi-layers of structing, right? To arrest the tilting movement, right? The outward movement of the retaining wall. So that's the blaze construction. You have the cantilever construction, you have the blaze construction, or sometimes you have the tie-back system. You know what's the tie-back? Well, if that is the retaining wall, it's a sheet pile wall, and then you have the tie-back again, right? In multi-layers of the tie-back system. Now this also will arrest, right, or hold up the movement of the retaining wall, the cantilever retaining wall, right? If the height is too high, the wall try to, is tilting upwards, or even moving outwards. So you have applied the tie-back system, the ground anchors or the tie-back system, right? So you apply the force, right, to counteract the tendency of moving out. Okay, now you have several terminology. There's the wall stem, right? It's a retaining wall. You got a stem, and then that's the base, right? Here's the toe, and that's the heel, right? Heel. Okay. The toe and heel, right? And then you have the stem. Of course, when you construct your retaining wall, you have to, excavate, right, up to this line, and then first of all you have to construct the what? The base first, right? One, and then you construct the wall stem, and then the backfill. Okay, you have to construct the base first, and then put up the wall stem, and then backfill. Okay, now here comes the very common types of the construction of different retaining wall in Hong Kong, right? First of all, you have the mass concrete. Now, it may not be rectangular. It could be looking like that, right? A trapezoidal. You have a larger at the base and a narrow at the top. And that's the prep wall. That's the prep wall. That is the precast beam, precast concrete elements, right? By stacking and interlocking of the individual precast concrete elements, you put up a frame, right? And then inside the frame, you put a backfill with the soil. Right? The Gabion wall, I've talked about that. And then you may have the reinforced field, right? The concrete, and then you have plastic, or sometimes steel tape. Sorry, steel tape. It's the steel. So, and then you infill with the soil particles, right? So that gives you the reinforced earth. Here's the word, right? Reinforced field, right? The the soil medium is reinforced with say the tape, steel tape, or plastic tape. Right? Now here you have at the back, right? If the wall is too high, so you provide, at the back, you provide a wing wall, right? A wing wall. So that's the wing wall. Wing. It's a wing wall. It's a wing wall, right? At the back, if the wing wall's at the back, it's called the counterfort. It's in the front, it's the buttress, right? Buttress, right? They are both 扶壁 okay? Buttress, 扶着 okay? And here's the cantilever retaining wall, okay? So can you follow with my explanation? Yes or no? Can you follow? Yes or no? Good. Now we come to the gravity retaining wall. Now, in gravity retaining wall means the wall will rely on the weight or of the masses to resist the lateral force, the active pressure, right, behind the wall, due to the soil and also as well as the surcharge, right, at the top. Now, the design of the gravity retaining wall will look into the overall stability, the overall stability. Now, there are three important failure modes of the retaining wall. So, three modes of failure. You have to guard against, right, these three modes of failure. Okay. The first one is the sliding. It means that the wall, right, under force, it will come to here, right? Come to here, right? Sliding failure. And what about the overturning? It means that the retaining wall here, right? You got a retaining wall here. If it's overturning, it means that the wall is overturning, toppling, right? It's rotation of the wall about its toe. And then you have the bearing failure. Now, what's bearing failure? The soil bearing failure. It means that the retaining wall here, right? Under a very heavy force, what will happen? The soil here may fail. In other words, the retaining wall will settle here. Settlement. Because the soil shears by fail, right? Because of the excessive pressure at the toe of the retaining wall exceed the soil bearing capacity. In other words, exceeds the shear strength of the soil. So the soil will yield, right? Will settle. So that's the bearing failure. That means the ground is not strong enough, right, to support the wall under the horizontal force. So you have to design the gravity retaining wall against three types of failure, right? Sliding, overturning, and soil bearing capacity. Mass concrete is the most simple, right? The simplest type of the retaining wall. But it can only retain a height less than 3 meters only. And crib wall are the assembled from the individual precast or prefabricated units, right? And then you have the free draining granular infill. You fill up the voids, the space with the granular material, and all together act as a gravity retaining wall, right? Because of the weight of the granular infill, so you can and then retained inside the frame of the prefabricated units. So this crib wall, right, will contain all the granular fill inside it. So it forms a very heavy gravity retaining wall. And now see concrete retaining wall, a very common type in Hong Kong. It resists if that is the RC. So if you take the moment about that point, so if it's under a, very heavy horizontal force, so it tried to, turn over, right, or overturn this, right? So you have to provide the weight of this soil, right, and the weight of this wall stem, and the weight of this base. So it tries to give you a what? A stabilized moment, right? The stabilizing moment. So it's clockwise, right? While here, for this one, it gives you a overturning moment, right? Here's the overturning moment. Overturning moment. If the stabilizer moment is greater than the stabilizer moment, if the stabilizing moment, right here, right, the clockwise moment is greater than the anti-clockwise moment, so it will be stable, right? So you have to design the RC retaining wall such that the restoring moment or the stabilizing moment will be greater than the overturning moment due to the horizontal force. And of course, you have to prevent not only overturning, but against the sliding as well as the soil bearing capacity. So you have no sliding, no overturning, and also no soil bearing. Right? And finally, you have to carry out the structural design for the wall stem and the base slab. So here, the ULS and SLS, right, for the steel reinforcement. Right, you have to check out whether any section of the wall stem or the base slab will be overstressed. So you have to put in adequate amount of steel bars, right? The main bars and also the distribution bar, so that the ULS and the SLS requirement will be met. Right? Here you have the, that's the counterfort, right? Counterfort. And here is the buttress, right? In Hong Kong, we have a lot of T-shape. So you have the inverted T, but here is the L shape, right? L shape. Which one is better? By having a longer toe here, it will give you what? A greater, a greater lever arm, right? And then you have this weight of soil. So it gives you a bigger stabilizing moment, right? Because of larger L, right? Here, for the L shape, this weight, smaller L, right? So this one should be better than the T shape, right? The inverted T shape is better than an L shape retaining wall. That's why in Hong Kong it's much more common, right, to have the T shape cantilever retaining wall. If the height of the retaining wall is too high, So you have to, right, to use a stronger support, either by counterfort or buttress. But of course, the disadvantage of these two types of retaining wall are the, a, a much larger space to be occupied, as well as the construction cost, right? It's quite expensive, right, to construct the counterfort or the buttress for the retaining wall. Okay, now I'm not going to repeat, right, all these details for the L or T shape and the counterfort retaining wall, right? And one interesting thing to note that for the here, say if there's the counterfort, or buttress, right? So any soil pressure, right, acting on this, the stem, right, wall stem. Now you can regard this piece. So you have, the soil pressure acting at the back of this wall stem. So this is regarded as a simply supported piece of slab, right, over the counterfort. So you have provide. So the spanning direction, right, that is this, the spanning direction, right. So that is the spanning direction, right. So the wall pressure will be resisted through the slab and transferred to the counterfort. And then for this counterfort, because the force is going to move outwards, so you have to resist a tension, right? So you develop a tension here. So that you are trying to pull, right? To pull this triangular piece of the counterfort wall into two pieces. So there's a crack here, right? So that's a tension cracks, right? So that is the, the counterfort retaining wall. You have to provide very strong reinforcement, right? The strong reinforcement to resist this tension, right? But for the buttress, here's the buttress, right? Here's the buttress. Well, behind the wall, you have the, the horizontal pressure here. So what happened here is the what? The wing wall will be under compression. So you don't need too much reinforcement here. You are utilizing, right, the compressive strength of concrete. So the concrete here will be under compression. It's good for concrete, right, to exercise its compressive strength. But here, you have the tension. So you have to use steel bars, right? And here you use the concrete. So in terms of design, right, the compression of the buttress retaining wall will be more economical, right, than the counterfort. Because in counterfort, you have to put in more reinforcement. Well, cantilever retaining wall, it could be either sheet piling, right, steel sheet piling, or soldier pile wall. Now, what is a soldier pile? You drive the, first of all, the H section, right? Steel section, H section, and you are going to excavate in front of the H section, and then you put either the timber planks or the precast concrete panels, and then do some excavation, and then put in right down below the individual pieces of the precast concrete panel or steel or timber planks. Right now, the soil acting behind, right here, right? Here's the soil, right? It gives you the concrete pressure, right? Sorry, give you the soil pressure. Suppose that's the soil pressure. So here, right, the timber plank will serve as a beam, right, to resist all this UDL and transfer all the loading to the left hand side and the right hand side. They are the steel section. So eventually, because under the action of this soil pressure, it will give you the bending of the steel H section towards outside, right? So it will move out under bending, right? When the excavation continues, right, down into the greater depth. So eventually all the soil pressure will be transferred through the timber planks, right? And then the timber plank will transfer all the loading to the steel section. And then the steel section, depending on its depth of penetration, driven into the ground. Eventually, this steel H section will resist all the horizontal forces, right? All the lateral forces behind this wall. Right? So that is the soldier pile wall. Can you see? Right? They look like soldier, right? Standing vertically, right, and firmly, right? The soldiers, the soldier pile, the soldier piles. Okay. 兵裝 okay. And these are the planks, right? So it consists of the vertical piles and the horizontal planks. Now you have to avoid the instability of the wall, right? For the wedge soil under the wall, so that will give you bearing favor, right? Soil bearing. And here's the overturning of the wall, right? It's rotating about its toe. And also you have to design carefully about the bending moment and the shear force in the structural members. To avoid overstressing, you have to choose, right, appropriate, the steel section or appropriate amount of steel reinforcement for the RC wall and so on. Well, ship piling, right? Ship pile wall. So that is still ship piling. it should be looking like that, right? So you have the interlocking here, right? Interlocking. So individual pieces of ship piling will be interlock each other, right? And these rows of steel ship piling, right, will be driven, right, into the ground. So here's the, the depth of penetration. Well, if the height of the retained soil is too high, so you have to input several layers, or right, multi-layers of the blazing or the tiebacks. Here's the blazing, right? The blazing, right? Levels of blazing, right? Or the tieback system, the tieback. So the tieback, right, will give you a pulling back force, right, to arrest, to stop the movement of the ship pile outwards. Right? And here, the blazing will give you the force here, right? If the wall is going to move out, the blazing will give you an opposite forces, right? So the blazing is actually utilizing a compressive members, right? The struts is under the compression, and tieback you are utilizing the tension of the steel. So it's a tension system, right? While the blazing is a compressive system. So you have to know sheeting, railing, and strut, right? So you have, the rows of the ship pile, and then you have the, right, the railing, and then you have the strut, right? So that is the sheeting, and then you have the railing here, right? And then you have the strut here, right? So vertical sheeting, horizontal railing, and also horizontal struts. Okay, the soldier pile. So here is the, here's the soldier piles, and that is the sometimes timber lagging, planks, or sometimes the leggings, right? Okay, leggings. Well, ball pile wall. I think you have come across what's the ball piles. So there's a ball pile. So you have, individual ball piles forming a continuous wall. Right? Of course, it's very expensive. Sometimes you may have to adopt the handle caisson. So it's done by hand. It's not by machines, right? It's very dangerous, right? the government will only approve this kind of method when they are convinced that that is the only method you can do, because you can't use advance at all. So it's a very dangerous method, right? On the other hand, all the power walls will be excavated and constructed by machines, right? Very heavy duty machine. So you have the power wall, the ball power wall, a very close spacing, right? They are almost packing each other to form a continuous wall. And you can see here you got the tie back, right? That's the tie back system. And also you have learned about the diaphragm wall, right? Under the construction technology and materials course, you have learned about what's a D wall, right? That is the D wall, diaphragm wall. So when you are doing some excavation and then infill with the bentonite, the bentonite, or sometimes called slurry wall. Well, the slurry will support the ground from collapse, right? Because you are digging a trench. And then after the excavation, you lower the reinforcement. You can see the reinforcement, right? The steel bars, cage. And then you use the trimmy pipe, right? The trimmy concrete, right? The concrete will be cast at the bottom of the tube, so it will flow out and then displacing, right, all the slurry out of the trench there. So eventually you have a RC structure, an RC wall there, right? That's called the D wall, the diaphragm wall, right? When you do this 1, 2, after then you have to do the 3, right? The interlocking one, right? So that it will give you a continuous wall. So you can see here, right? There's a circular diaphragm wall, right? And the excavation at the top photo is the grab machine, right? Which will be the hydraulic grab, which will be excavating the soil, right? For a D wall, for a diaphragm wall. Okay, can you follow with our discussion? So do you understand what I've been talking about? Yes or no? Okay. So you don't got lost, right? Anyway. Now we come to the more difficult part of this chapter, the analysis and design of retaining wall. Of course, for the design, you have to think about the ULS and the SLS, right? But for the purpose of this course, we concentrate on the ULS. That means we have to guard against our wall from the stability failure, right? From any sliding, overturning, or from the soil bearing. Right? So remember these three things, right? Overturning, and then sliding, horizontal line sliding, right? Horizontal sliding, overturning. And then the bearing capacity of soil, it means settlement, right? Are there any soil, right, fails under the vertical loading? Well, for sliding, there are a few factors of safety recommended for the design of the walls, for the retaining wall. So we are talking about here, right, for the new walls, for the new construction, sliding, factor of safety against sliding, right, is 1.5. Factor of safety against overturning, right, is 2.0, 2. And then factor of safety against bearing failure is 3.0. Okay, so 1.5, 2.0, and 3.0. We are talking about 1 to 10 years, right, of return period for the rainfall, right? It's good enough, right, to incorporate these factors, recommended safety factors, right, into our retaining wall design as recommended by the code. Right? Now we will come to the different example, right, of this factor of safety analysis for the retaining wall. 8.1 in your teaching notes, 8.2 and 8.3. Now for the RC retaining wall, for the massive or the gravity retaining wall, you have to check three things, right? Factor of safety against overturning, sliding, and soil bearing. Now what about for the other types of retaining wall, say RC retaining wall, concrete retaining wall? Now you can not only rely on the self-weight of the gravity wall, because here it's not a gravity wall, for the here, right? It's very thin, right? It's not, the weight is not too high, right? It's not that heavy. So you have to rely on this piece of soil, right? So when you are going to analyze, right, for the RC retaining wall, you have take into account the weight of soil here. It will retain. It gives you a stabilizing effect, right? I have told you before, right? We have discussed that. Not only the weight of very thin wall stem and also the weight of very thin base, well, you have to use this weight, right? Now that will give you a very good stabilizing effect. So that's why you have to, the cell weight and also the what? You have the soil, right? And sometimes you use the shear key. What's that? If you're going to slide towards to the left, then you can, use this shear key. Now, what's the advantage of using this shear key? Because you have a, when it's going to move out, then you have built up a very heavy and high passive soil pressure acting towards to the right, right? Okay, so here you have the active force, active pressure. If it is very high, this force will be very great. But once you incorporate the shear key, you have a a pretty good, right, passive pressure, right, to counteract the active force. So that's the purpose of using a shear key for a RC retaining wall. Okay, but you have to pay attention. Suppose you got a retaining wall here, right? And you have a very typical, sometimes the shear key here, right? And you have this here, right? Now suppose you are going to dip a trench here. What will happen? Because you are digging a trench in front of the retaining wall, so you got all the passive pressure, right? Got lost. So the original horizontal resistance has been completely lost due to your trenching works. So this wall, under the horizontal force, will, under this, it will go either, right, sliding or overturning, right? Overturning. So this wall will go out, right? Because of your trenching work, because you have excavating the material out of your trench, so there will be no passive pressure, right, developed. You got loss of this passive pressure. So that will affect the stability of this retaining wall. So you have to take due care, right, for any trenching work next to your RC retaining wall. You are undermining, right? You know the word undermining. You are undermining the stability of a cantilever retaining wall. Okay. Now let's talk about the surcharge, right? What's the surcharge? It means that if there is a retaining wall, right? Sometimes you may have a surcharge here. Surcharge. Well, in the Geo guide, you have to design for a minimum discharge minimum 10 kilonewton per meter square, right? So this will give you a not only, you know, the active pressure due to the, you know, the Ka gamma H, but you also give an additional, right? So you have give you the additional surcharge, right? Additional pressure here is equal to the Ka, if that is the surcharge is Q, so Ka_Q, right? So 10 kilonewton per meter square times Ka. Okay, so that you have to pay attention to the surcharge, right? So that is the additional lateral force, right? So you not only PA1 and then you got PA2 due to the surcharge, right? That's the surcharge. Additional pressure due to the surcharge. Now, what about for the passive earth pressure due to the shear key? Well, it's not that difficult because when you know if that is small h, so what is the pressure here? And you know the pressure coefficient, the passive state. So Ka gamma h is here, right? The pressure here. Ka gamma h. Now, what's the total force there? And at that position should be h over 3, right? And what's that force? P equals to what? Kp gamma h times h over 2, right? Kp gamma h squared. So that is the total force, right? This big resultant force, right? The passive resistance, right? Given by this depth of soil, h. Of course, you know what's Kp? 1 plus sine phi over 1 minus sine phi, right? What's Ka? Ka 1 minus sine phi, active state, 1 plus sine phi. You should be very familiar with these two words, right? Active pressure coefficient and passive pressure coefficient. Well, we'll come back to the example 8.2 in the lecture notes. Now, anchor sheet pile wall. As I've told you, you got the tieback system, right? Okay. Now, saw anchors or the tieback system. Why we should use the anchor sheet pile wall? Now, imagine if you got a very site long, right? Now, if you are going to install the bracing, right? Now, that's tedious, right? Say if that is, say, your site's 100 meters. How can you transfer these forces, right? How can you transfer these forces over 100 meters in compression? Now, that's tedious, right? So why not use this system? Why not use this system? The tieback. So you have a very clear, right? You have a very open and wide, clear site, right, for all the working within this site. But for the above, you have loss of working space here because of the multi-layers of the structuring, right? So compare the two, right? Anchor sheet pile wall will give you a better working space in the excavation site. Of course, one disadvantage is that you have to install, right, this anchor, this tieback. Adjacent to your site. Now, if you have only the construction site within this limit, in other words, the tieback system may go beyond the boundary of your site. Now, you have to seek the approval, right, from the adjacent neighborhood, right, or whether the tieback will interfere with the foundation system. If there is an adjacent building here, you got the building here, right, and they got, you know, the foundation, then you have to install the tieback interfering with the foundation, existing foundation of the adjacent properties. Now that could be a very troublesome, right? Or you may not be permitted to do so. Well, for this system, I could talk a little bit about it. Now that's the anchor head. Anchor, tie back. So you have to provide this force. And then you have the active pressure here. You know, you got the water pressure here, right? And then a water pressure there because you got the water table here. So again, you got a water pressure. And then you have the passive pressure, right? The passive. And here the active. Here's the active. Okay, you have to consider the equilibrium for this vertical structure under the different horizontal forces given from the water or also from the soil. In front of the wall is the passive pressure, and behind the wall is the active pressure. Right? Well, we'll discuss 8.3 later. Right? So, place and structure excavation. Right? I've told you. Right? The basing means, right, you got a ship pile, and then you have the wailing and strut. Right? Okay, so that is the strut or place the excavation. Right? So the name of the vertical is the king post, and here's this horizontal struts. Right? King post, right? King post, and here is the horizontal strut, right? Of course, it gives you the support for this soil pressure behind the wall, right? So provided, you know, the structuring will provide the force, right, to resist, right, the soil pressure behind the wall. So it's under compression, right? It must be under compression, right? The place structure. So the sheeting, right? These are the sheeting, and that's the wailing or whale, and that's the strut, right? That's the strut, and that's the wave or the wailing or whaler. Now the analysis of the placed ship piles is given by these three diagrams. What are they? Well, for the, you know, if there is a wall under different level of struts, right? That's the placed excavation. Now, what's the pressure, soil pressure acting on this wall? Now, it could be divided into three cases, right? Case A4 is for sand. So, a very uniform soil pressure acting on behind the wall is given by this equation. Is equal to 6.65 gamma H, right? Times tangent here, right? Times tangent square, bracket 45 degrees minus 5/2. what about for the type B, soft to medium clay, right? Sorry. And here's for the soft to medium clay, right? Clay. You got a trapezoidal distribution. For H, the triangular distribution will go through this 0.25H, and the rest will be uniform. And what's the pressure there? 0.3 gamma H, or this one, right? Gamma H bracket 1 minus 4C over gamma H, right? Whichever is the greater, right? And then for the very soft to for very stiff clay, or fissure, right? Or fissure clay, it means with some cracks there, stiff and fissure, it means cracks. Then you can apply this, trapezium, right, sort of distribution. 0.25H, and the top 0.25 and the bottom 0.25H will be triangular distribution. And this is 0.2 gamma H to 0.42 gamma H, okay? Now, in calculating now remember that this diagram serves to calculate the struck forces. In other words, we want to know, right, how much is it? How heavy is the loading here? Now, it's a statically indeterminate structure. It's very difficult to analyze this structure, but here are some simplification. Now, you can assume there's a hinge here, right? But not for this one. The top one and the lowermost one will not be a hinge. So you come back here, you got, right, this is a structure, right? So you got a structure there, right? So you can work out, right? What's the force there? FA and FB1. And then you compare the other one. For this one, very easy, right? A beam under UDL. So you got FB2, right? Here's the FB1 and FB2. So you add these two things together, right? That will give you the struck forces here, FB. Okay? In other words, the FB will be equal to this force, FB1 and FB2, right? That is the, here, right? You have FB1, and here you got what? FB2, right? So you add these two all together to give you the forces in the struck B, right? So similarly, you can work out the FC, right? FC. FC is equal to FC1 and FC2, right? FC1 is here, right? FC1, okay? And FC2. So you add these two, give you the FC, okay? It's quite a easy job, right? Now, before we go into the detailed calculation, now, could you raise any question about this chapter 8, right? Earth retaining wall or earth retaining structures. Any question for this chapter apart from the calculation? So can you follow the lecture? Is that okay? That's the, the descriptive part rather than the calculation part. Yeah, sure. Except the calculation, as always. Any question? No? That's good. Well, we will leave this PowerPoint discussion, okay? Now, can you see the chapter 8, the Word file? Can you? Yes or no? Can you see the Word file? Okay. Now, let's take a look. Example 8.1. Well, that is a trapezoidal gravity retaining wall. Right? Now, you have to check out several things first, right? What's this? The unit weight of concrete. Okay? Unit weight of concrete. And you can see here a little bit difficulty because you got a sloping angle, right? It's not horizontal. Beta 15 degrees, right? And then you have the mu, right? The coefficient of friction at the base, 0.55. And then the maximum soil bearing capacity is 700 kPa. So whenever the soil is stressed greater than 700, there will be an excessive settlement, right? So it will be regarded as a fail. Okay. Now, I don't want to go into the detailed calculation, except outlining the design principle, right? Now you know the height here, right? And all these dimensions. So you got W1 here, W2, sorry, W3. So W2, so that is W2. Oh, so that is the width, right? Okay, I will not use the W then. Now you can work out the the individual weight, right? So F1, F2, right? And then the F3, right? Okay. Now before the calculation, you have to work out the Ka first, because beta is equal to 15 degrees, right? So what's the friction angle of the soil? 30, right? 30 degrees. And gamma, 18, right? So you put the beta, right, 15 degrees, and also the friction angle of the soil, 30, into this expression. So you got the Ka. Ka is equal to 0.3729, right? And you have to work out this height, 1/3. Now, of course, it's not 6 meters, a little bit higher, right? You got this 6.16 meters, right? So the vertical height about the hill of the retaining wall is not 6 meters, it's 6.16 meters. Okay, that is your H, right? And then you work out the total force PA, right? So you got 127.38. Because it is a sloping force, so you have to resolve this force into two components, right? You got the vertical component and the horizontal component. Of course, the horizontal component is the PA times cosine 15 degrees, right? So you got 123. And the vertical component is 32.9 something, right? And then you have the component 1. So what's the area of the triangle? Here's the area of the triangle, right? Here, right? Triangle area is 6 meter times 1.2 meter divided by 2 is the triangle area, right? You have to multiply it by 24 because it's the unit weight of concrete. So similarly, you can work out 1, 2, 3, right? 1, 2, 3 is about the concrete. And what about here? 44 is the soil, right? The unit weight of soil is 18 kilonewton per cubic meters. So it's talking about this piece, right? That is the soil, right? Here's the concrete. Okay, then you have to take moment about the toe. Remember that the toe, you have, because it's rotating about that point, right? It's rotating about that point, the toe. So what's the force here? Right? Say here. So if you want to calculate the moment about this toe, so what's the distance here? The D1. D1 will be equals to 2/3, right? 2/3 of 1.2, right? So what's the distance here? Right? 2/3 times 1.2, okay? And what about here? What's the distance here? 1.2 plus 0.6, right? So you got all these distance, right? The moment arm here, right? The moment arm here, right? 1.2 plus 1.2 divided by 2, okay? 1.8 for the element 2 and so on, right? So you can work out all these moment arm. And then you multiply these two, give you that, okay? So multiply that by 2.8, give you that. So you add up all this moment. It is the soil, right? So 684.35554 is the stabilizing moment. It's about clockwise, right? It's rotating about the. Now, what about the overturning moment? We have worked out 684, right? And this overturning moment, this one, right? And the overturning moment is equal to what? Right? The horizontal force, right? Here, right? 1, 2, 3 something. And here is 1/3, right? Above the bottom. So 123.04 times 2.05, right? Okay, 2.123. So give you the overturning moment. So the restoring moment is bigger than overturning moment. It gives you this ratio. So it's greater than 2, though that's okay. Right? So we have checked the, the overturning moment. Right? Check the overturning stability. Now, what's the sliding force? What's the sliding force? The pH, right? The pH is the sliding force. 1, 2, 3 something. So that is the sliding force. This is the sliding force. Okay. Now, what is the base friction? Well, it's equal to mu times the, the friction law. Is the vertical weight. What's the vertical weight? Here, right? That is the vertical weight. The vertical weight, vertical force, downwards, right? So that's the N, right? So that's the mu, right? 0.55 times give you 202. Well, the friction is greater than horizontal, right? 202.75 over 123. Now, give you a factor of safety, 1.6. So it's bigger than 1.5, right? Okay. Remember that the factor of safety against overturning should be what? Greater than 2. Against sliding, 1.5. And soil bearing pressure should be greater than 3, right? So let's take a look. How to check the soil bearing pressure? Right? Now, for any section, you got a section here. For any, sorry, for any section, if that section is under an actual force, N or P, and then moment. So that is the P, and then the moment, right? Now, what will happen for the pressure under the P? And also the section under a moment. Now, it will give you this sort of distribution. Okay, P over A. Okay, and what about for this one? Here. So it gives you a triangular distribution, right? So eventually it gives you, so it gives you a smaller force here, right? But a sorry. Suppose that's suppose that is, you know, let me take some figures. Suppose that is 100. And if that is, you know, 60, right? So that is 60. So eventually this will become, sorry, if that is 50, right? So this one will give you 10, right? 60 minus 50, right? 60 downwards, upward 50, it gives you 10, right? But here, what will you get? So 60 plus 50 give you 110, right? 110. In other words, whenever it's a section is subjected to a axial force, so it gives you P over A. And what about for the moment? It gives you my over I, right? Remember that very famous formula, sigma over y equal m over I, right? That's the beam formula, right? M over I. So everything talking about the moment, right? About the center, about the center. So about the C here, right? About the C here. So we're talking the moment about C, right? So how are you going to work out the moment about the center line C? So you have take the individual moment, assume, right? Here, anti-clockwise positive. So first of all, 86.4. So this one, right? 86.4 times what? We are talking about the moment about C, right? So it's equal to 1.5 minus 0.8. Why is that? Here you can see, right? You're talking about here 2.4. So there's 3. So that's 1.5. 1.5, right? So here, right? Because you are taking about this point C. So what is the distance between this center line and the centroid of this triangular element? So it gives you what? It's 1/3 of 1.2, right? And what about here? That's 1.5, 1.2, 1.8, 1. 0.6 is equal to 1.8. 1.8 minus 1.5 is equal to 0.3, right? So the distance between the centroid of the element 1 and the center is equal to 0.4 plus 0.3 is equal to 0.7 meters, right? Okay, 0.7 meters. So you can see here, 0.7 meter. Okay. So it's 0.7 meters. Okay. Now, what about the element 2? For the element 2, here, element 2. For element 2, okay, the center here is here, right? So what's the distance between? So what's the distance for this D? What's the distance D? Well, this one. 1.2 divided by 2.6, right? And here you got what? 0.6. So it's 1.2, right? 1.2. And then you got 1.5. Again, that should be equal to D. 1.8 minus 1.2. 1.8 minus 1.2 is 0.6, right? 0.6 meters. So this, the distance D here, here, should be equals to 0.6 meters for element 2. So you can see it's for element 2, is that right? 0.3 meters. Oh, sorry, it should be 0.3. Yes, it's equal to 0.3. Why? Because from this point up to there is 1.5, right? 1.5 minus 0.6, 0.6 is equal to 0.3. Okay? So eventually, for all the other elements, you can work out is 121.09. You can see it's positive. In other words, it should be anti-clockwise. So that's the M, right? And that is the my over I. That's M y over I, right? Of I is very easy. 1 over 2 times 1 times 3 to the power 3, right? 1 over 12 B H to the power 3, right? B is the width, 1 meters, right? And the base is 1.5 meters, sorry, 3 meters, right? 3 meters. And Y is equal to, 1/2 of the 3 meters. So it gives you 122.8 plus or minus 80. Right? Now remember that because it gives you the counterclockwise, right? So we believe that so you have this. So that is 203.6 kPa. That is sigma maximum. And here's the sigma minimum. 122 minus 80 equal 42 something. 5 kPa. So there, the toe will be under a higher soil bearing pressure. Okay. Now, of course, we are interested in the sigma max, right? Because we are concerning about whether the soil will be able to bear the pressure or not. So 203 compared with 700 give you a factor safety greater than 3, so it's okay. And what about the minimum? The minimum is again 42. Anyway, it's greater than 0, so there will be no tension. Okay? If it's negative, it means that the soil will be under tension. Okay? Is that clear to you? It's quite a difficult one because you got a trapezoidal retaining wall rather than a rectangular or the other simple types. Okay, can you follow? Do you? Can you follow the calculation steps? Yes or no? Okay or not okay? But the point is to take the moment, right, at the center of the base. That's the key issue for this calculation. I think the checking bearing pressure is more difficult among all the 3 modes of failures, right? You have to work out the. Yes, you're right. But by doing more practices, it's not that difficult, right? Because you have to be careful about the lever arm calculation, right? The centroid of the individual components, right? And the distance between that point to the center line of the base, right? I think if you have gone through the example 1, 2, 3, then it should not be that difficult. It should be difficult at the start, right? But after you work out for several trials or several examples, it should not be that difficult. So any question? Now I want to give you a 5 minutes break, right, before we come back for the tutorial, right? Is that okay? 5 minutes break. Could you hear from me? And also, can you see the Word file on your screen? Yes or no? Cannot see anything. Okay. Can you see the tutorial 5, the Word file? Okay. So could you hear from me? Okay, that's good. Now, this is the tutorial 5. You need to hand in the assignment 5, right, in the next week. I mean, Tuesday, right, is the deadline. The next Tuesday is the deadline for submission of the tutorial assignment 5. Now, to save my workload, I'm not going to acknowledge the receipt of your assignment, except that I will, I've, after I've marked your assignment, I will give you back the marked assignment to you, okay, in a single return email, okay? Now, may I remind you again, please follow the exact file name format, right? So for the next submission is A5 underscore your name and then underscore your student number. Is that clear? And please hand in the single file PDF file only, right? Do not break the file into several number of files, right? I need to, recombine it. Now you are wasting my time. Please observe my instruction, right, in the submission, please. Okay? Yes or no? I need your confirmation. Okay. Now we come to the tutorial assignment 5. There are 2 questions. Now I will try to give you some hints, right, in completing the assignment. So please listen very carefully, right? Now you got this retaining wall 5 meters high, and you got the soil parameters shown on the right hand side, and there's a water level, right, 3 meters deep groundwater table behind the retaining wall, and the coefficient of friction between the base and the soil is 0.55, and the maximum soil bearing capacity is 300 kPa. Right, that is a typical figures for Hong Kong, particularly adopted by the Highways Department. The bearing capacity should be about 300 kPa. Right. Now, first of all, you have to work out the pressure distribution behind the retaining wall. Well, we believe that now what's the pressure here? Say P1. And what's the P2? What's the pressure? Well, you have to work out the horizontal pressure coefficient, right? Active pressure, 1 minus sine phi over 1 plus sine phi, right? Equals to what? 1 minus sine 32 and 1 plus sine 32, right? So it's equal to 0.307. Now what's the P1? P1 is equal to gamma H, gamma, right, times 2. Right, 0.307 times, that's the Ka, gamma H, gamma is equal to 17.3, H is equal to 2, right? So give you P1, 10.63 kPa, right? So it's 16 point, sorry, 63 kPa. Now what about P2? Well, it's equal to, on top of P1, you have the Ka times what? The total stress minus U, right? So what's the total stress? $19.5, right? Plus times 3 minus 9.81 times 3. Okay, that is the, the effective stress, right? But of course, that is the effective stress. But you have to work out the pore water pressure, right? Pore water pressure 9.81 times 3, right? So that will give you a total of 49 kPa. So that is 49 kPa. Okay? So that is 0. Okay? So that is sigma dash plus U, right? you have to work out the effective stress first, right? And then times the Ka. And then you have to add the water pressure here. So it gives you 49. Now, can you work out the force here? F1, F2, and F3, right? What's F1? The area, right? The area. Then you have this. Okay. So F1, F2, F3. It's very easy. Of course, I cannot do the whole calculation for you, right? You have to work out the area of this, right? Yellow triangle, the green rectangle, and the triangle in purple, right? So you can work out the area. And then can you, that's the D1 and the D2 and the D3, right? Now that's the overturning forces, right? Okay. So can you work out the overturning moment? F1 D1 plus F2 D2, F3 D3, right? Now it's not that difficult, right? What's the D1? It's very easy, right? D1 is equal to 3 meters, right? 3 meters, right? That's the 3 meters. And then it should be 1/3, right? 1/3 of the 2 meters, right? Because it's, the centroid is 1/3 of the height. So 1/3 of 2 meters plus 3 meters, that's the D1, right? What's the D2? Very easy, right? Because it's 3 meters, so it's 1.5 meters. And what's D3? D3 is equal to 1/3 of 3 meters, right? So I'm not going to repeat that. Now, what's the restoring moment? If you divide it into 2, so that's the W1, and that's W2, right? So what's W1? W1 is equal to what? 24 times what? Right? The yellow triangle, right? What? Half of the base is 4 meters, and the height is 5 meters, right? So that gives you the unit weight, or sorry, the weight of the W, right? And what's W2? 24 times what? Oh, sorry, it should be not 4 meters. The base is not 4 meters, right? It's 4 minus 0.6 meter, right? The base of triangle, right? And then times 5. So that is, 4 minus 0.6. That is 0.6, right? So what's the area of the rectangle? 24 times 0.6 times 5, right? So you got the total weight, W1 plus W2, right? And what's the overturning moment? Sorry, the restoring moment. Restoring moment. The restoring moment. The restoring moment. The stabilizing moment is equal to W times what? The L1 plus W2 L2, right? What's the L1? What's the L1? That's about the toe. So what's the L1? And what's the L2? L2, right? Of course, L1 is equal to 2/3. Right? Here's the 2/3. 2/3 of what? 4 minus 2/3 of 4 minus 0.6, right? 0.6, right? And what's L2? L2 is equal to 4 minus 0.6 plus what? 0.6 divided by 2. Okay? L2 is equal to, 4 minus 0.6 plus 0.3. So you got the restoring moment. Okay? Now, you got the factor safety against overturning, MRS over MOT, right? So if that is double star divided by the star, double star over star, give you the factor safety against overturning moment. Now, what about for sliding? Okay, chest sliding, right? What's the sliding force? What's the sliding force? F1 plus F2 plus F3, right? So you got the area of that components. So sliding force is equal to summation of F1, F2, and F3, right? The sliding force. So what is the friction resistance. Right? Friction resistance. R is equal to 0.55, right? The mu times the, right? Because you have got the W1, W2, right? You got here, right? W1, W2. So that's the normal force. So once you know the W1, W2, so the factor of safety against sliding is equal to what? The resistance divided by the sliding force, right? It should be something, is it greater than 1.2? Right? So is it greater than 2.0? Right? If it is the overturning safety factor greater than 2.0, there should be no overturning problem. If the factor safety against sliding greater than 1.5, there should be no problem with the sliding. Okay. Now, when it comes to the checking bearing pressure, right? So bearing pressure. Now, if you take the moment about the midpoint, so what's the midpoint? About the midpoint, okay? So where's the midpoint? Here's the midpoint, right? Two meters, right? 2 meters, the midpoint. Now, the moment of all the forces, F1, F2, F3, about the midpoint are the same, right? So the moment about the midpoint due to the horizontal forces is always anti-clockwise direction. Okay, so the overturning moment will give you the anti-clockwise direction. Okay, now what about for the midpoint here? The midpoint somewhere here, right? So you have to work out the, here, the midpoint. The midpoint is here, right? Now, what's the distance between here, right, and that here? Okay. Now, let me take a look. That is 0.6 meters, right? And you got the midpoint here, right? So what's the base? What's the base length? 4 meters, right? So 2 meters, 2, right? What's here? 0.6 meters, right? And that is so is 4 meters, so 3.4 meters. Okay. Now, what's the centroid here? Right? Say the W1. What's the W1? Here's the W1, right? And that's the W2, right? So if you take moment about this point, now what's the centroid here? 3.4 meters, right? Times 1/3. It gives you 1.133, right? So the centroid, 1.33. Now, what's the width here? It's equal to what? 3.4 minus 2, right? This would be 1.4 meters. In other words, the centroid is somewhere here, right? The W. Now, what's the distance? The D equals to what? That is the D. It's equal to 1.4, right? Minus 1.33 meters, right? Is equal to 0.07 meters, right? Now that gives you the W1, D1. What is that direction? The clockwise, right? About the moment C, right? The moment C here. Okay? Can you see here, right? The centroid is equal to 1/3 of 3.4 meters, right? So it's 1.3 feet. And that is, that is 1.3 feet. And that is 1.4, right? So it's equal to the 1.4 minus 1.3 feet. So give you the, the clockwise moment. And also here, what about the D2? The D2 is here, right? The D2. Okay. Okay, D2. Sorry that something is going wrong. I have to restart my application. Sorry for that. Sorry that I could not fix the problem. So could I leave the tutorial 5 to you? Now, please take the note that now when you work out the, can you hear from me first? Now, when you calculate the, for the checking the soil bearing capacity, you have to take the moment about the middle of the base, right? Okay, not about the toe. For checking the overturning about the overturning, you have take moment about the toe, right? Now, because when you are checking the safety factor against soil bearing, you have to work out the moment, right? The P over A, right? P is the normal force divided by the area, right? P over A plus or minus my over I, right? Now, the moment M there, you have to take the moment about the middle of the base, okay? Now, about the whether clockwise or anti-clockwise, depending on the location of the centroid of the, the triangle or the rectangle, right? If it's on one side is the clockwise moment, you have to take it as clockwise, right? If the location appears on the other side, that will give you anti-clockwise moment. So take it anti-clockwise, right? So when you're adding the clockwise moment as well as the anti-clockwise moment, you will obtain a net moment there. Okay? Now that moment is the value of the M, right? In that soil bearing formula, right? My over I. Is that correct? Right? Y is the half of the base, right? If the base 4 meters, right? Y is equal to 1/2 of 4 meters. So give you 2 meters. Okay? So the trick, right? Or the key to catch is the distance between the centroid or the individual components, right? The rectangle or triangle. The distance between the point and the center of the base. Now, which will give you the different lever arms. And different lever arm will give you the different clockwise or anti-clockwise moment. So you got it? Yes or no? Okay. So you got my points? Yes or no? half. Because all the Word document or even the PowerPoint do not respond in my computer, so I cannot, write anything in front of you. No file could be opened. I don't know why. Okay, now let me check about this. Now, can you see the PowerPoint? Can you see the PowerPoint? Yes, okay. Okay, I write something on it. Suppose you got, can you see the drawing? Could you see the drawing? Yes or no? Okay. Now, you are the centroid here, right? The W1. And you got the centroid here, W2, okay? Okay? Now, here. Oh, sorry. Now, if you take the centroid, the center, right? The center. B over 2, B over 2, okay? Because you got the B here, right? Now, if that is the D1 and that's the D2, now can you tell me when you take moment about the center, about center of the base, can you work out what's the distance here? L1. What's the L1? What's the moment for W1? Is equal to W1, the moment, right? For W1 is equal to what? Is equal to what? W1 times what? What's L1? What's the L1? How can you calculate the WL for L1? It's equal to what? B over 2 minus, right? D1 over 3. Is that correct? You know here, right? The centroid here, right, is equal to 1/3 of D1. First, I make a larger joint, okay? Okay, much larger, okay. Okay. Now, use the figures, okay? There's, 2 meters. There's 1 meters, okay? So it gives you 3 meters, okay? Now, W1. That's W1, and that's W2, right? Okay. Now, if that is the midpoint here, right? The midpoint, 1.5 meters. That's 1.5 meters. Okay. Now, what's the centroid here? What's the distance here? What's D1? D1 is equal to what? Equals to what? D1. Here, the D1. Now, it's equal to, first of all, you know what's this distance? 1/3, right? 1/3 of 2, right? The triangle is 2 meters here because it's 1/3, right? So that's 1/3. So that is the M1. So M1, okay. So in order to work out the D1 is equal to what? That is M1, right? M1. So can you work out the D1? Can you work out the D1? So it's equal to 1.5, right? Minus, okay. So it's equal to 1.5 minus 1, right? So 1.5 minus 1 is equal to that, right? So minus M1, okay? It gives you the D1, right? What's M1? M1 is 1/3 times 2 meters, okay. Okay? Can you see the D1? Now let me repeat. D1 is equal to distance between the middle of the base and the centroid, right? W1. So that is the D1. It's equal to 1.5 meters, right? 1.5 meters minus 1 meter, right? Minus M1. Is that correct? What's M1? M1 is equal to 1/3 of 2 meters. Okay? See the point? So the moment, WD1, is that clear? Okay? Now, what about for D2? What's the here? What's the distance D2 here? Can you work out the D2? W2 D2. Now, what's D2? Center here, right? What's this? What's the distance? 1 meter divided by 2, right? Okay. And then you got what? The total distance, 1.5 meters. Right? Okay, let me repeat, right? Here, right, 1 meter, right, 1 meters divided by 2, right? Because it's 1 meter, it's a, a rectangle. 1 meter divided by 2, right? And then you got 1.5 meters minus that. So 1.5 meters minus 1 divided by 2 give you distance between this point to that point, right? So that is your D2, right? 1.5 meters minus this piece, right? Okay? Yes or no? So that is the skill, right, of determining the distance, the lever arm, right, between the centroid to the center of the base. And then you have to note the direction of the moment, clockwise or anti-clockwise. Okay? If you regard the counterclockwise moment as positive, so every clockwise, counterclockwise moment will be positive, and anything clockwise moment will be negative. Okay? The W1, W2 could be on the either side of the center of the base. That is the trick, right? So everything is clear. Now, good. Then I will stop here, right? So you should be able to work out, the soil bearing failure. And also you can try this method with respect to the example 8.1, 8.2, and 8.3, right? Okay? Okay, then I will stop here. The calculation of the lever arm is a bit trivial, right? So you have to employ your skill of calculating the distances only. Once you got the care and the skill, it's not that difficult, right? It's a matter of calculating the distances. Okay? Then I will stop here. Okay, and say bye you all.